Swayam Prabha. Digital India. Educated India.
Okay, so welcome to the 6th session on this refresher course on structural analysis. So we had started the topic of beams. If you see, the title is Internal Forces in Beams. And usually in a beginner's course in structural analysis, we straight away go to find the internal forces. What are the internal forces? At any section, you have a bending moment and a shear force. But what do you lose in that approach? That's a normal approach we do. It's an approach which is focused on statics. You lose an appreciation for the kinematics. So we don't want to do that. We don't want to rush into left brain operation. We want to see what's going on. We want to understand what a beam is. And if you remember in the last class, you defined a beam as a structural element which is subject to bending. And it resists external loads, typically applied transversely to the longitudinal axis of the element by bending, by developing bending moments, and also shear forces. That's it. We did not define the beam as a horizontal member. Sometimes people say it's a horizontal member. Not necessarily. It can be inclined, it can be vertical. All right, so let's proceed. Remember, we asked a question at the end of the last class, and I hope some of you worked on it. Do you have the answer to this question? We said we'll first take a case of pure bending, but not the pure bending induced by an externally applied moment. This is bending which is happening naturally. How? Through a temperature change. Just like if you have an axial member, or say a rod, and you keep it on a frictionless surface, and you increase the temperature of the rod by, say, delta T, then you know that it wants to increase in length, and it will increase in length by L alpha T. There is a thermal strain which is alpha T, alpha delta T. Alpha is the coefficient of thermal expansion. Now, if I want to induce bending in that member, then I can do that by giving it a thermal gradient, and we did that. If you remember, here is a cantilever beam, and it has a rectangular cross section, and we increase the temperature at the bottom by T and reduce the temperature at the top with a thermal gradient such that at the centroidal axis there's no change in temperature. So every fiber gets to change the length, either increase in length or reduce the length exactly the way it wants. There's no external restraint to prevent it from changing. Just like we had the case of the bar on a frictionless surface. So above the centroidal axis, all the fibers want to reduce in length, and below, all the fibers want to increase in length. And because it's a linear thermal gradient, every fiber can increase or decrease the way it wants by the cantilever beam curling up, bending up. This is classic bending, but there's no stress. There's no bending moment, there's no shear force. So, nice example to see bending. Just to understand what bending is, and we said that this will typically bend as an arc of a circle with a certain radius of curvature. This radius is same everywhere, and if you take the top length AB has now become AB dash, which is L minus L alpha t, and the at the soffit of the beam CD has changed to CD dash, and the length is increased by L plus L alpha t. This is obvious. We reached here, and this is called sagging. Sagging doesn't necessarily mean you have a positive bending moment. It means it's sagging. The curvature is like this. We call it positive curvature. And you're told that the depth of the beam is 2a. With this information, can we work out an expression for the radius of curvature? What's the answer? What's the answer you got? Okay, the answer can be derived very easily. The tangent drawn at any point on the beam will be perpendicular to the radius at that point. Okay, here it's horizontal. And if you take a location y above the centroidal axis or the neutral axis, we'll find fibers above have contracted, fibers below have elongated. Then the radius will be, because you're now drawing a tangent like that, the radius will be r minus y. Correct? And the strain on this is simply given by the change in length by the original length, which is, if you say that the angle subtended by this beam, the two ends, is theta, then very simply this arc is r into theta at the centroid, and r minus 1 into the same theta divided by r theta. That's the original length. This easily reduces to minus y by r. Why do you get the minus sign? What does the minus sign indicate? You got contraction, you got a compressive strain, which is y by r. What does this tell you? The r is a constant, right, for this entire beam. Y changes with the location vertically across the section. When y is equal to 0, there is no strain. When y is equal to a, if you go up, then it is the maximum compressive strain is minus a by r, and at the bottom you have a tensile strain and elongation plus a by r. Very simple, simple basics. Now logically you might be tempted to think that if you multiply this with the modulus of velocity, you will get a stress, but that's a wrong way to think. Why? Because there is no stress here. This is a thermally induced curvature. Just like you don't multiply the modulus of velocity to L alpha t here, to alpha t. Why? Because it wants to increase. Only if you prevent it from increasing in length, you get a compressive strain. Are you getting it? A compressive stress also. So that's called an elastic strain. This is not an elastic strain, this is a thermal strain. But the definition is the same, change in length by the original length. And the other thing you see is epsilon in the x direction is proportional to y. So it's a linear strain profile. You can see it matches so this is your linear variation in elongations and contractions. So we've already seen this. Now if you substitute the values here, y becomes a, and at this location we already know that the change in length is L alpha t, right? So from this you get the simple proof. I don't know how many of you got it right? Just 1, 2, 3, 4. Okay, you didn't try, right? Or you're too shy to say you got it right. Now just check the units. Whenever you get answers, always check the units. R has units of meters. All these look funny. A is also meters. Alpha is It's a strain per degree Celsius, and T is degrees Celsius. So everything is fine. This is radius of curvature, and we already discussed this. The definition of curvature is phi is equal to reciprocal of radius of curvature, having the units of meter raised to -1. Got it? Good. Now, there is something called deflection. Now, we will define deflection with a positive sign when it's in the positive y-axis. So, it's gone up. So, deflection is delta of x. And so, this is delta. If this is the location x, this is delta of x. And slope or rotation is the slope when you draw a tangent here. That's theta of x. These are standard definitions. Okay. There is no bending moment, no shear force, pure geometry. Right? We have a clear understanding of bending. Yes?
So suppose if we keep the beam as some individual plates, plates by plates, and if you apply the same process, the bottom plate will expand, the top plate will compress, and the shape will be like a trapezium.
Sorry?
If we cut the whole beam into some plates, and if we do the same process, there will not be any bending, right, sir? It will be trapezium shape.
Yes, if they can slide relative to one another without any friction, yes.
So here, which means there is some horizontal shear stress generated.
You don't need stress, no?
Here, how that bending actually...
It's a good question. Incidentally, you have the same phenomenon when you study curvature in beams, shrinkage in beams. You have the same problem. So he's raised a good question. He says, why can't it all be straight and this become like that? Any answer? That's possible. But what do you think will happen? Theoretically, yes. If you cut it into separate pieces, that can happen. But can this also not satisfy the curvature? Somewhat. So, you have a flexural behavior here. Let's ask another question. Let's say I applied a moment here. Let's say the curvature is caused by a moment. So, should I apply the moment anti-clockwise or clockwise to get this behavior? Anti-clockwise or clockwise? Anti-clockwise, right? What happens then? Will you get exactly the same behavior or not? Will you get exactly the same behavior or not? Is it also not a case of pure bending? Yes or no? So this is what actually happens in practice. It curls up. Okay? You will get same behavior. Do you have any shear in pure bending? So there is no friction, no need to apply any glue, right? So there, what you're saying is might happen if you break it up into separate things. But if it's one homogeneous thing, this is a equally likely and more likely possibility. Okay, good question. But maybe you should do an experiment to see with your own eyes what happens. All right, so let's summarize what we did. So we'll try to understand curvature with respect to the strain diagram. This is a strain diagram, right? These are the elongation diagrams, contraction diagrams. The strain is this. Top strain is contraction alpha t, bottom strain is alpha t. And so you can talk of, by equating these quantities, we already proved them, we can, from this derivation, you say from the strain diagram itself I can get curvature. From the strain diagram, because these equations match very well. So this curvature, phi, is theta by L. So remember this, always you can, if you know the strain distribution, if it's a linear distribution, you'll get the curvature at any section by this simple definition. And if you take d theta and ds, you can define ds as r d theta, small element, and 1 by r can be defined as d theta by ds equal to phi. So you can see that theta and phi, curvature, rotation and curvature are related like this. Now we make an approximation. We make an approximation that ds and dx, the projected length in the x-axis, for small deformations are nearly the same. And when you make that approximation, we say phi is equal to d theta by dx. The actual derivation, the definition for curvature works out to be this. You probably studied this, but this is can be approximated as this because this quantity d delta by dx itself is very small. So very small quantity, much less than 1 fraction. If you square it, becomes even smaller, and so in the denominator this is nearly 0, in which case this quantity becomes 1, and so you get phi is equal to d squared delta by dx squared, right? So you've got nice relationships between curvature, rotation and deflection, which we'll use later. No bending moment shear force in this derivation so far. So that's it, you're familiar with this. Now we take the same beam and apply the moment. Now we'll try to generalize and say the section need not be a rectangular section, but it has to be a prismatic section for our definition here. Let's give it a trapezoidal shape. The cross section everywhere is this trapezium, which means the centroidal axis is not in the middle. In the previous case it was in the middle. It will be slightly below, you know that, right? Now in simple bending theory, which is how we normally learn bending, we say that the centroidal axis is the neutral axis, yes or no? Can you prove it? Again, once upon a time we had learnt the proof, but now let's prove it. It's a very simple proof. How do we prove it? Well, we know that, first of all, how do we reduce this three-dimensional beam to a line element? We are making many assumptions. What is one assumption that we make? The assumption we make is, at any section, wherever you cut the beam, whatever cross section you got will go up all together, go up or down, right? Without any transverse bending. So that's one requirement. There should be no transverse bending. Let's say you are designing a ramp, say in a hospital building, you always have to have a ramp, and you want to economically do it, so you take the parapet also, let's say parapet and the waist slab are one, so it's a channel. Now why don't we treat this channel shaped element as a inclined beam? You can, but you have to be careful. It's not the same as this because there is going to be some transverse bending. It's not just longitudinal bending. Do you understand what I'm saying? So if you don't have transverse bending, this will just vertically move up or down. So that's one assumption we are making. So if you take a section at A and you blow it up, the centroidal axis is likely to be there. And let's say here again we are assuming the same radius of curvature. It's exactly similar to the previous picture. Here this is induced by a force, by an action. Earlier one, no force was applied. Same situation, the cross section is like this. This is A is equal to r theta, and the centroidal axis is also, so there is an axis, we are assuming it's a centroidal axis. We call it neutral axis because there is no change in length after bending, no strain, okay? R theta, A equal to R theta is the same. That's what we call the neutral axis here, or more accurately the neutral plane, because it's actually having two dimensions, in the x and in the width dimension. There is no stress there. So if you take a location y and you go by the same definition, you will get the same definition for strain, but this is now an elastic strain. And so Hooke's law will operate. And what is Hooke's law, by the way? What does Hooke's law state? Within the proportion, did he say proportional limit? In an elastic body, or like a spring. Actually, the studies were done on a spring. You pull down a spring or you compress it, it's going to increase in length, right? So, or you take an axial element, because spring will have torsion in the smaller. Take an axial element, you pull it down. The stress, the normal stress, is directly proportional to the strain. Is there anything more to Hooke's law from which we can say that the force applied is proportional to the change in length? There's something more in Hooke's law which brings in the definition of elasticity. Unless you say that, Hooke's law is not complete. And when you unload the specimen, it must come back to the original position by the same path. Then only it's complete. It must. So you understand. So we are not getting into Hooke's law, but you're familiar with that. So you have a modulus of elasticity acting, and so this is your stress. Because the strain profile is linear, we've already seen that, and because the modulus of elasticity is a constant, the stress profile is also linear. How do you say that? E is a constant, R is a constant, only Y is a variable across the depth of the section. And this kind of behavior we call sagging, when the fibers below the neutral axis elongate and the fibers above contract. Now let's get into the proof. Why is the centroidal axis the neutral axis? So let's give it a three-dimensional look. We are able to reduce this cross section to one point here in the line element because of certain assumptions. One assumption we make is that at any distance y, all the deflections are the same. They'll all go up together the same amount, which means we are saying that the strains are all the same. At any depth above or below the neutral axis, the strains are all the same, and therefore the stress is all the same, and so you need not look at the cross section. You can treat it as a point on a line axis. All right. But if you look at the stress block is like this, and 3D it will look like this, and we've already derived an expression for it, and you are applying a constant moment m, a sagging moment, let's say. That's your neutral plane or neutral surface. And if you take a small element dA in this cross section, obviously it's self-equilibrating. There's no axial force, there's no normal force in this entire cross section. So if you sum up all the forces in the x direction, they should all add up to 0, but here you'll have to integrate because this is a continuum. And so this is fair to write, integral dx sigma x dA is equal to 0. You substitute for sigma x with the formula we derived and pull out the constants. E by R is outside, and so you end up with this property. So to satisfy equilibrium, you are saying that the neutral axis is located in such a place where this is actually the definition of the centroidal axis. The moments of the areas about that axis is 0. Right? This is purely an area property. This y bar is the location of the centroidal axis. Got it? Whatever reference you put. So No stresses involved here. This is a pure geometry issue. I might as well ask you, you've done limit states design, right? In reinforced concrete design. There is this true at the ultimate limit state? Is the neutral axis the same as the centroidal axis? Why not? Give me the clear answer. Stress strain profile is not linear, so not only stress strain profile is not linear, we are saying the concrete has cracked, concrete will take no stress. You remember? And so the whole concept of this equation is not valid anymore. E is not there. It's become non-linear. Here you're making one more assumption. You're further making the assumption that you have the same constant of modulus of velocity in tension and compression. In reality, that's also not true, except in steel. So a lot of embedded assumptions are there in this simple bending theory. You're assuming the material to be homogeneous, elastic with the same elastic constant. All right. So, but if it is not, then also you can work out accurately. You should know how to do it. All right. So since A is not 0, y bar is 0, that means your reference axis is the centroidal axis, right? Okay. But we have one more equation. If you take moments about the z axis, then the externally applied moment or the bending moment at that section plus this is 0. And so you can get this equation. Y squared comes into the picture. That's the second moment of area. It's also called Iz. It's again a property of the section. And so you have this famous equation. M by EI is curvature, is 1 by R equal to phi. And so if you substitute, you have this famous Euler-Bernoulli equation, which in the last class you just vomited out. You will never forget it. M by I is equal to E by R is equal to sigma by Y. Right? This is just a refresher for what you did. We'll move on. So this is sagging. Very nice, simple picture. You can see that. Now, if you look carefully, can you draw the bending moment diagram for this guy, for this loading? He's standing with 2 feet, right? So what kind of bending moment diagram do you expect? Is this pure bending? You draw one curve like that, it looks clean, pure bending. It's not. In pure bending, what is pure bending? We gave you 2 examples. One, kinematically induced, the other, statically induced. What is common to both? No, pure bending. What is common to? Along the entire length of the beam. This is your left brain fixated thinking. First one, was there any shear anywhere? No. That's also true, but I want a kinematic answer. First, you see. What do you see? Do you see shear? No. What do you see? Yeah, what do you see about the curvature? There's something nice and special about the curvature. It's a part of a perfect circle. So the radius of curvature is constant. That is pure bending. If it's impure bending, so will you get this having part of a circle? No. For the reason you said also, because there is some shear involved. So let's say this beam I put lines on it before this fellow stands on it. On the side I'll make some lines like this. Then let's see what happens. Well, actually his 2 feet I can put as 2 point loads. Yes or no? So this is a loading. It's a simply supported beam. This is a free body. It's actually not a loading diagram. It's a free body diagram. And you see what's happened to the straight line, the vertical lines and the horizontal lines. Okay? Vertical lines, what do you see? Ideally, everywhere. Will they be straight or will they be inclined? What's your view? In other words, will there be any warping? Well, there will be. We'll look at that a little later. But if I cut a section here, in this region there's no bending. That's pure bending. So in this region it's clean and there's no shear. There's a couple of compression and tension separated by a lever arm Z. And the equilibrium says C is equal to T, which is a couple, and the C into Z or T into Z is the bending moment at that section, right? We know this to satisfy equilibrium. That's how we define bending moment. Nobody can see a bending moment, but what you can see is fibers getting into compression, fibers getting into tension. There is a resultant compressive force at that section, resultant tensile force. They form a couple, and the couple has a magnitude. It's called bending moment. It's an internal moment. It's not externally applied. The internal becomes external the moment you expose it, which is what we do in a free body. We are freeing it from constraints. Okay, so we've got that understanding of bending moment. And there is also a shear force at a section to the left of it. And there is a shear stress distribution for a rectangular section. What is this shape going to look like? You've studied this. It's going to be parabolic. How do you say it's parabolic? At the top and bottom, the stress has to be zero. Why? Okay, to prove it's parabolic, what do you have to do? So normally we, especially when you do reinforced concrete design, we say V for shear, right? V says it's vertical force, because we are assuming the beam is horizontal. That itself is wrong. Here we'll use S because it need not be horizontal beam, it can be inclined beam, but traditionally V for shear, vertical force, right? Will you be able to prove, okay, why is the shear stress zero top and bottom? With the vertical stress idea, you won't get it. So you have to look for the complementary shear stress. Complementary shear stress will be in the other direction. Why is the complementary shear stress, in this case the horizontal direction, zero at the top and bottom? Because it's a free surface. Unless you have a traction applied there, you won't get. So stress here is zero, stress here is zero, and if you take a section there, you will get a shear stress. What is the value of this stress there? 1.5 V by cross-sectional area. How do you get that? More generic formula? Okay, so we won't get into that. Please, that's VQ by IB. Alright, but let's try to understand what happens to these. I want you to physically understand. I've taken, actually these are points there, but I've taken a small segment, say a square piece from here, here, and I'm going to see how those things are going to change. So in pure bending, you will just have changes longitudinally. There's no distortion. Agreed? These 1 and 2 will elongate sideways and 4 and 5 will contract sideways. Agreed? Here, this is a typical cantilever. Here, the compression is in the bottom and the tension is on the top. It's a cantilever, classic. And this is the deflected shape. In this case, these lines will be perfectly straight. This is the plane sections remain plane assumption in pure bending. You can actually see it with your eyes. If you mark those lines, they will be absolutely straight. Now, and you know this, now if you apply, instead of a moment, you apply a force here, the deflection overall will still look the same, but what's going to happen is, in this region you will get maximum shear stress. So if you have only these two arrows, then you won't satisfy rotational equilibrium of these elements, so you have complementary shear stress. You will get some. So what will happen to this? You can imagine that this diagonal is going to be made longer, and this diagonal is going to contract. Got it? So this is the condition of shear, and you could, if they are equal, in this case, you could say that it's a condition of pure shear stress there, which you could equate to tension and compression, right? So if you take the principal stresses, it's as though this diagonal is subject to pure tension and this diagonal is subject to pure compression. But what shear does is it distorts the section. What bending does is it preserves the overall geometry, it only elongates or contracts. So shear is a distorter. That's why it creates problems. Okay, it likes to distort the section, and the distortion is less here progressively, and here it is least. Here at this, it's still not zero because we didn't take at the top. At the top, it's going to be zero. And similarly at the bottom, you'll have a distortion like this. So that's the difference between this behavior and this behavior. And what happens is you'll have warping of the section, slight warping. Is it clear? All right. The shear is constant here. So the shear strain is constant everywhere in this particular example. All right. And this is how the shear stress vary. Now we'll come to the main topic. What are internal forces in a beam? So typically, let's take this sign convention. A beam is subjected to some distributed loading, and the loading has an intensity Q, kilonewton per meter, Q of x at a location x, so Q of 0 here. And this is the sign convention we'll take for shear and moment. Okay, left side up, right side down is the sign convention for positive shear. Sagging moment is the sign convention for positive bending moment. And so with this sign convention, we are saying this, one look at this and we say this is sagging, and the same radius of curvature everywhere. So we say bending moments are positive and curvature is also positive when you have a shape like this and moments applied like this. If you reverse it, then we say this is negative curvature. This is a sign convention commonly used. We say hogging. This is hogging and this is sagging. Similarly, shear, though you may not know this too well, and this is the formula, we know that. Shear, if there's a rotation like this, typically when the left shear is acting up and the right shear down, you actually have a shear strain gamma, which is having a clockwise rotation. And if it's a constant shear, this will be straight. Similarly, if it moves the other way, we say it's negative shear strain, negative shear force. Are you getting it? So here we've discussed the sign convention of not only the force, but the corresponding deformation. Clear? All right. And there is a relationship. Look at here. Always there is a force and there's a material property, which is the modulus of shear rigidity G, which is related to E, you know that in terms of Poisson's ratio. And you have a dash. We don't write A because there's a correction for the shape. Because the shear stress is non-uniformly distributed. So this you may not use much, but this is something that you always need to use. Now let's just go through the basics which everybody learns. Standard drawing, you're given a simply supported beam with a concentrated load. We've already learned how to find the reaction. We know many methods to find the reaction. Very simple logic that this reaction, will this reaction be more than this or less than this if A is less than B? Left reaction will be more, and very simple. The fraction of W that goes here is B by L times W. The fraction of W that goes here is A by L times W. We know that. All right. Now we are going to go inside. First we look at shear deformations. Now forget about bending. Actually we ignore this in normal deflection calculations. There are two components to deflections. Deflections caused by shear and deflections caused by moment. Deflections caused by shear are usually ignored because they are relatively small in well-proportioned beams compared to deflections caused by moment, by bending. In some cases they cannot be neglected. In which cases? When the depth of the section is comparable to the length or close to the length. Say if the length is 2 times or 3 times or even 4 times the depth, then don't ignore shear deformation. If it's 1 time, definitely don't ignore. But if it's a beam like this which looks well proportioned, span by depth ratio is about 10 or 12, then you can ignore this. This is all exaggerated. Whenever we draw deflection, it's like drawing caricatures. We are like cartoonists. We blow up the deflection to make it really visible. But the main thing to know is, because the shear force in this region is constant and this region is constant, the shear strain is also constant up to here, and the sign convention is there. So these are deformations greatly exaggerated. Actually this is going to be very small. But the real deflection, so if you look at shear alone, if you cut a free body, let's cut a section here at some location X, this must satisfy equilibrium, this must satisfy equilibrium. If the overall structure is in static equilibrium, every part of it must also be in static equilibrium. So with that argument, we say that the vertical reaction here is already known, and if I cut a section here, I'll get a shear force. Downward is positive, so it's equal to the reaction at the left, and I have a moment here which is the bending moment we'll look at. I could look at the free body on the other side. So we had a reaction here and we had a load here, so this must be the difference between this and this, but you'll find that's true, this is more than this, so this plus this must be equal to this, so this must be equal to the same reaction here. So whichever way you look, you get the same answer but equal and opposite. When you join them together, all these fellows will be vanishing. Now why is this equal to this, equal and opposite to this? Correct answer from the earlier classes. Which law? Which law? Newton's third law. You understand? Because this comes from contact. This comes from contact. So that's why this and this will be equal and opposite, this and this will be equal and opposite. They come from contact forces. But separately, this is Newton's first law. Equilibrium is satisfied here. All right, this is free body. When you cut a section here, if you cut a section on this side, it gets reversed, and the shear here is WB by L, and it's negative. Same argument, okay, because of our sign convention. You're familiar with this. So if you have to, I want to know in one diagram the shear force at any location in the beam, so I need a distribution, right? That's called the shear force diagram. It's a simple diagram. I've got my equations, and so more interesting, the shear inside the beam at the support section is equal to the reaction. But because of the sign convention, you will say at the left it is equal to the value of the reaction at the left. It's the same sign. At the right, the shear force will be equal to this with a negative sign. Are you getting it? This comes from our sign convention. Left up is positive, right down is positive. Is it clear? So remember this thumb rule. And so your shear force diagram, you don't need to draw a y-axis, is always going to look like this for this beam. Positive shear in this portion, negative shear in this portion, constant. Because the shear force is constant, the shear deformation will follow a linear profile. Clear? This part is normally not taught, but at least statics is clear. Okay, we'll move on because this is WA by L. This entire stretch on this side up is WA by L. Correct. Good. Next. Bending moment, similarly, if you apply equilibrium, you can derive an expression for m of x here. M of x is this into this distance. By the way, the deflected shape is like this. This is what we are familiar with. Certainly for this proportion, the deflections caused by bending are going to be the real deflections. Caused by shear is very, very small. Alright, so you have elongation at the bottom, tension side, compression side. So our thumb rule is we will draw on the tension side. So from this equilibrium, you can prove moment here is WB by L into X, and moment here is WA by L into X. You can look at the free body, which is easier to analyze. So when you look here, this is a little more messy because you've got to subtract. This is easier, so always take the easy one. IIT students always take the shortest path. So, but you can work out the hard way here, you'll still get the same answer, right? So this is bending moment, and you'll find there's a linear variation, and you can draw it either like this or like this. Okay, this is drawn assuming your y-axis is up and bending moment. This is how in first year sometimes you learn like this, but as you grow older you'll say I'll draw it on the tension side. This is the tension side. There's a reason for this, I'll show you that. Is it clear? And the maximum value is exactly under the load, and what is the value? W AB by L. Just substitute x equal to A. It's a linear variation. Now it is because this is linear that your shear force is constant. We'll see that. Alright. So we've come here. Now let's take, this is strictly not a beam. What is this called? This is called a frame. Maybe imagine you're playing basketball and the net is up there and somebody made a frame like this, right? And you've seen pictures of these American basketball players, they sometimes hang on the basket. So imagine one fellow is hanging on the basket, and so that's his weight. Got it? Now it's instinctively you feel it's going to bend like this, right? Now there is going to be bending moment in AB and BC. So we are moving a little ahead beyond beams into frames. Now, where do you have only bending moment and shear force? In AB or in BC? In BC. You have only bending moment and shear force. In AB, you have something extra. What is that extra thing you have? Axial force, which is compressive. That's the only thing that makes it a frame element. Now, if you really want to analyze this, you can find the reactions here if you want, but let's not find the reactions. Let's start from the free end. Always it's nice, easy to start from the free end. So if you separate out AB and BC, they will look like this, right? You start from the free end. I have a P acting there. At this section, I have to satisfy equilibrium, so there must be a P acting up and a moment acting like this, whose value is P into L by 2. Equilibrium is fully satisfied. Sigma Fy equals 0, sigma M is equal to 0. Got it? No question about that. Now, bring in Newton's third law. This B is common to this part and this part, and so by shear contact, whatever you put here, you have to put here equal and opposite. Simple, Newton's third law. So P down and moment clockwise. Are you seeing? And then here you will get the reaction straight away. Here equilibrium has to be satisfied, so this P down must be matched with the P up and this clockwise moment with an anti-clockwise moment, right? Simple. Very simple. No complication. This is statics. And now you have to draw your bending moment diagram and shear force diagram. So this is how you draw the bending moment diagram on the tension side. You see, for this element you can talk of sagging and hogging. Now this is going to deflect like this, so it's tension on top. Clearly, it's a cantilever. So you can put a minus sign there and draw it there. But for this vertical element, some people put minus sign here also. You can't say anything. Why? Is this sagging or hogging for the vertical element? The deflected shape is like this, no question about that. But is it sagging or hugging? If it's tilted, you can still say from below, from above. But vertical fellow, what can you do? You say, no, I am standing here, this is to me hugging, so I'll put a minus sign. Then you better tell the person who's reading your menu that I am standing here, my reference is here. But it gets complicated if you have a multi-story building, you don't know where you're standing. So that is why we say you don't have any confusion, you don't need to write plus or minus, always draw on the tension side. Now, if you have tension at the top corner here on this beam, you're bound to have it at the same corner in this element. Right? And so if you need to put reinforcement in this reinforced concrete column, your steel is really needed at the top here and on the left side here. The same bar can go right through. Are you getting it? So one look at this diagram and I know where to put my steel if it's reinforced concrete. Got it? So this is how you draw bending moment diagram on the tension side. But to be consistent, if you're drawing it on the compression side, on both the elements, you should draw on the compression side. It's a sign convention, like driving on the roads. If you're crossing over from London to Paris, all the rules change. The left side is correct in England and the right side is correct in much of the rest of the world. Okay. So that's it. Tension side, compression side, free body. You can see clearly the tension, the green color on this side and the compression here. Is it clear? That's just to give you a feel. So you get this feel only if you bring in kinematics. Now you see the deflected shape. This, you can say, must be part of a big circle. Why? Because you have pure bending here. Pure bending with some axial compression. But not for this. In this, you have bending moment 0 here and maximum bending moment here. So this, the radius of curvature is going to change. Is it clear? Okay, we move on. In beams, you have kinematic variables. We already looked at this. What are they? 3 of them. And they are related. First, you have deflection. I'm saying sagging is positive, moving up is positive. Then you have slope. The very word slope says it's a slope of reflection. So that we call delta. Slope is theta. Theta x is the derivative of delta with respect to x. Right? Then we have one more. What is that? Curvature. Curvature is best understood in terms of radius of curvature. And that radius can theoretically change from point to point. Whenever the radius of curvature changes, what does it imply? There is some shear coming into play. There is shear coming into play. Otherwise, it should be the same. Okay? So, curvature phi of x is 1 by r, which is the second derivative. This is approximate. This is the exact definition of curvature. You remember the formula for curvature. For small deformation, you can take this approximation. That's it. Now we talk of static variables. Remember, this is the family of, we gave it a gender, feminine. This is masculine. So you have a load intensity Q of x. We said upwards is positive. Then we said the shear force is there. Okay, positive sign convention, S of x. And we say a bending moment, M of x. Just like these 3 are interrelated by maybe, who's the grandmother here? Deflection or curvature? Deflection. Because slope is the derivative of deflection. Slope is the daughter of deflection. And curvature is the granddaughter of deflection. Derivative, it is derived. Here, who's the boss? Who's the grandfather? Here, bending moment must be the grandfather. See, it's got the maximum weight, kilonewton meter. Okay? So let's see the relationship. To see the relationship, you draw a small element, cut a small element here at some location x, and very small at the distance x, and we say that yes, there's some load intensity Q of x acting here. There's a shear force. We'll take the positive sign convention up here, and let's say the shear force is changing potentially by delta x, and the moment is also changing, sagging mxn. This could be 0, need not be 0, let's see. Apply simple equilibrium. Sigma y is Fy equal to 0. You will find that this delta S must be equal to Qx into delta x. Right? And if you take to the limit delta x tending to 0, it turns out to be dq by ds, dx. dq by dx is s. So this is a relationship. Similarly, you can prove by saying that this delta x is very small. You can prove that the shear force is the derivative of the moment, and this brings a relationship between the males in the family to the females in the family, right? What's the relationship if it's due to elastic behavior? We already saw this. M by I is equal to E by R, which is E into phi. So curvature you multiply by EI, you get bending moment, or reverse, bending moment you divide by EI. EI is called flexural rigidity, you get curvature. Once you've got this, you can get these, and once you've got this, you can get these. So that's how the game is normally played. We'll revisit this many times, but 3 basic variables in kinematic variables in beams and 3 static variables in beams, and they are all potentially varying with the length of the beam. All right. Now, if this is EI double dash, because this is the derivative of this, very easy to see, kilonewton meter and kilonewton. So your dx takes off the meter, and then this will be kilonewton per meter. Are you getting it? So this will be the 4th derivative. So this is often said to be the fundamental differential equation of a beam. EI into the 4th derivative of deflection is the load intensity Q. That's how you learn at an advanced level. But at a lower level, we are happy with this definition. Both are correct. That EI into the 2nd derivative is M. Both are correct. This is a little more advanced. If you have this, you can generate all of them. If you have this, you have to work on it. Is it clear? So these are the basic differential equations for bending in beams. So if you look here, these are differential relationships. These are derivatives, right? This is a derivative of this. 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 Got it? That's a relationship. Now, you can work the other way. If you integrate, you will get the parent. If you take the derivative, you will get the child and the grandchild. How do you do that? So at every point along the beam line, the slope of the shear force diagram is equal to the intensity of applied load, and the slope of the bending moment diagram is equal to the shear force. How do you do that? This is your fundamental relationship. From this, if you want to bring out shear force, you have to integrate this, okay, from say origin to x, and you use some dummy variable, and you get a constant here which has the units of shear force, some boundary condition. Similarly, for moment you can write like that. And you can also show that the difference between the values of shear force at 2 points on the beam line is equal to the area of the loading diagram between the 2 points. This is coming from fundamental definition of derivatives and integrals. And you can also take one step further and replace shear force with bending moment, and then this instead of loading diagram you get shear force. So it's the same logic. So look carefully at the integral relationships. Curvature is phi. If this is your starting point, and often this could be a starting point, if you've got bending moment and you divide by EI, you got this. If you want slope, you have to integrate this. If you want deflection, you have to integrate this or do a double integration of this. Similarly here, if you have the load intensity, shear force you get by integrating this, and bending moment you get by integrating this, and curvature you get by dividing this by EI. Are you familiar with this game? So we'll just take one traditional example. Practicing engineers don't play this game. In fact, they you know the old joke. You know, all you know is the Excel sheet, and you will never forget your basic arithmetic. What is that? Addition, multiplication, hopefully, subtraction and addition. But integration and all, okay, basic integrals you can do. But I think as good engineers, you should know when to use a tool and when not to use a tool. So let's take this example. Now, if you're starting from scratch, you will first, you got a loading diagram like this, you have to write an expression for q of x. This is what you'll say. In this region, say 0 to L by 2, you will write qx is equal to minus q naught, because your definition for q in the previous slide was positive upward. So this is acting downward, it's a constant load, and there's no load acting here. So the total load, you can say, as a practicing engineer, always good to say the total load. How much is the total load? Half q naught into x, and how much will come here? How much will come here? Can you quickly tell me? How much of W will come here? 3/4 of W will come there, and 1/4 will go there. That intuitively you should know. Okay, you can work it out. So you can find the reactions, and then once you know the reactions, you know the shear force in the beam at A and B. The shear force at A must be equal to this, same sign. Shear force at B must be equal to this with the minus sign. Got it? This much we learnt. With this boundary condition, you can play the game. You know that there will be an equation in this region, and there will be another equation in this region. So let's start with this region. For this region, you can blindly apply the integral relationships and move from 0 to x, and you can substitute CS. So you can see, you got this to substitute for this constant. You know one solution. So at x equals 0, you know the answer. Substitute that boundary condition, you will get this equation, right? Similarly, you can get the bending moment by integrating this expression. Again, you will get another constant, and you know that the bending moment at this location is 0. That's another boundary condition you know, so you apply that boundary condition and you will get this equation. It's always good to write these expressions in these non-dimensional terms here, always, because it's easier to draw and you'll have a feel for it. You can see straight away that this is a second order polynomial, a quadratic expression. This is a linear expression, right? And you can find the value here at x by L. You can find out what is the shear force here, the sign of it, and what is the bending moment by plugging in your values. I am not saying you should do this as practicing engineer. This is how as beginners we do. And for the segment CB, you can either work from right to left, or if you continue like this, you can work like this and then plug in your values and go through the same process, integrate, etc., etc. You will get another expression for your shear force and your bending moment. Okay, you're beginning with this as your boundary condition at x equal to L by 2. Got it? You can do this. But I strongly suggest don't do all that. That's for beginners. You are now, this is a refresher course. We do it the easiest way. What's the easiest way? Free body and equilibrium. How do you do that? You got the reactions, right? Then if you want an expression for shear force, very simple. This sigma Fy equals 0, this must be equal to this minus q naught into x. One shot, no integration. That's it. And this moment is this into this distance minus q naught into x by 2. So you will get the same answer much faster. I've given the final expression, but that's how, in reality, it won't be expression, it'll be some 10 kilonewton per meter and 3 meters and all. In one jiffy, you can get it. Is it clear? Similarly, for this side, I will take a section here, starting from the right side. And, okay, I want to find out, I want to find out where my bending moment is going to be maximum. How do I find that out? Shear force is 0. Shear force changes sign. Shear force 0. Let's say it's at some distance x bar. So I just put this equal to 0 and I get x bar is equal to 3 by 8 into L. Actually very easy to see. VA is 3 Q naught L by 8. It's acting up. And so it's, as you go further, it's going to get less and less. At some point it's going to become 0. When x equal to 3 by, so to find x bar, all I have to do is to divide this by Q naught. That's all. I divide this reaction by Q naught, I'll get x bar. That's 3 by 8 L. So my shear force diagram will look like this, straight line, flat, constant here, and my bending moment diagram will look like this, quadratic and linear. All my expression there. So this I can do. And I can also get the value of the maximum moment. Yeah, I can get the value here by substituting for x bar and get the maximum moment. Okay, done. Simple stuff. We have to stop for today. We will continue in the next class. Thank you.